Request everyone to switch off their mic, please.
We should take it back. This man killed our father, then stood at his wake and lied to our faces. It was a disgrace to the badge you wore. The one you were going to wear, the one I wear every day. This scumbag got
an ka je ba su san kuɗin you assess the patient kuma haifa ba su bane kaga wani irin level na wani status ne amma ka a yi resistant a ce ma ba a yi ba san kuɗi to dai juyo ko kiran wanda ya aiko ku kun ce mishi ga
Okay, good evening, everybody. Welcome once again to another session. Record on this computer. Okay, can you see my screen?
Yes, we can see variable.
Yes,
Okay, all right.
variable.
Okay, so good evening, everybody. Welcome to another session, part 2 of statistics. Yesterday, I think I got a mixed bag feedback. Some people understood, some were more confused, and some were struggling even with a little more basic concepts. So today I've tried to put a couple of slides before I continue the presentation. I've just created a few more slides to give you some more clarity and then help you along. Now, the most important thing is please shut your microphone, because otherwise I will get disturbed. I'm not familiar with this subject, so I have to concentrate, okay? It's not my home ground. Okay, so one of the feedbacks which we got from all of you is that people are struggling with a little more basic concepts of statistics. So the parametric and non-parametric tests were a bit difficult for them to understand. So I have taken a step back and I've even started trying to explain to you what is a variable, okay? So we'll do a couple of slides about variable, we'll do a couple of slides about parametric and non-parametric tests, where to use it, and then we will carry on. Somebody take over as a host. Who wants to take over? So Vikas, are you with us, or is Shilpa with us? Hello.
Yes.
So you can
Shilpa,
give host.
We both are
yeah.
there.
Okay. One person. I'm going to make you the host, Shilpa. Okay.
Mm-hmm.
And so whenever this microphone rings or whatever, just can you make sure they stop it? Yeah.
Okay. Yeah, sure.
Okay. Just you take control of that, because I need to focus on the slides.
Yeah. Okay.
Okay. So now you are the host of the show, so you can control everything. Okay. So as I said, a lot of people are struggling even with some more basic concepts. So let's first define what is a variable. So I just use some terms which I assume that people would know. So variables are structures, are fields in which the characteristics that differ. Okay. So they are characteristics that differ from subject to subject, from time to time, and they're called as fields. Okay. So data that you record into an Excel sheet, each cell of an Excel sheet is a variable. Okay, it's as simple as that. So each cell of the Excel sheet is a variable. All right. So guys, what is happening? Yeah, it's impossible. Just mute everybody. Shilpa, just mute everybody. Do mute all. Okay. So each cell of an Excel sheet is called as a variable. So whenever I use the word variable, it means I am referring to a data point. Okay. So variables are characteristics that differ from subject to subject and time to time. Okay. Data that you record into an Excel sheet is of two types. Okay. Whenever I use this word, you must understand. One is called as a numerical data, and the other one is called as a categorical data. Numerical data is made up of numbers. Okay, so age, weight, number of children, shoe size, etc., etc. Categorical data is made up of words. So eye color, gender, blood type, ethnicity, etc. Now, numerical data can be two types again. It can be either continuous or it can be discrete. Okay. And when I say continuous, it means there are infinite options. It can go from 0 to infinity. Okay, that is called as continuous data. So age, weight, blood pressure, this is all continuous data. It's numerical data, but it is infinite. As opposed to that, we have discrete data. Discrete data is something which has got only.
Don't fall back, fight on. We will finish this. We have done it before and we will do it again. సరైన కృష్ణదేవరాయ కొంతమంది సోల్జర్స్ ని పంపిస్తారు. That will come to fight చేయడానికి.
Shilpa, you are able to unmute people?
Sandeep, iPad, please.
I am muting them one by one, literally one by one.
Just do mute all. At the bottom, there's something called as mute all. Just do it.
Please unmute yourself.
Yeah. Hello? You can't hear me?
Yes, we can hear you. Please go ahead.
Okay. All right. So data that we put into the fields is two types. I'm just going to repeat this because this is the basis of all conversation. So statistics, when we talk, the language is different. So if you don't even know the language, if you don't know what I'm talking of when I say continuous data, then you're going to struggle with all the tests. Okay. So data that is numerical and categorical. Numerical is made up of words. Categorical is made up of numerical is made up of numbers. Categorical is made up of words. And then numerical data is continuous, something that has infinite options. And discrete has finite options. Only a finite number of cases can be put into that sample size. On the other side, categorical data is ordinal and nominal. Ordinal means it has got a hierarchy. So one is better than the other is better than the other. Okay, so from top to bottom, there is a clear-cut hierarchy in that data. And nominal is it doesn't have a hierarchy. It can be anything, random. So eye color, brown, black, blue, green. There is no hierarchy. Not that brown is better than black or better than. So pain severity is mild, moderate, severe. Okay, hierarchy. One is lower than the other is lower than the other. Okay, so it's a hierarchy. Whereas here, nominal data is there is no hierarchy. These just words which make up each cell of an Excel sheet is could be a different word. So that is the difference. So whenever we talk about all the tests that we do, remember these are the words which are going to come to you: continuous data, discrete data, ordinal data, and nominal data. It's a very simple concept. Okay. So now let's look at what are the differences between parametric and non-parametric tests. I think people are very confused yesterday. So let me talk about non-parametric tests. Non-parametric tests can be used on ordinal and nominal scale data. Okay, you know these two words now. Okay. Parametric data is mainly used on interval and ratio scale data. Okay. Non-parametric can be used on small samples. Parametric is used on larger samples. Most important, this is the most important, I told you yesterday, non-parametric is used on not normally distributed, which means skewed data. Parametric should fit a particular distribution. If it doesn't fit a particular distribution, your results will not be accurate. But there is a scheme within statistics where skewed distribution can be made to fit a normal distribution by using a log of the value. Okay. All right. This can be used where samples are not selected randomly. Okay. Here the samples have been drawn randomly from a population. Okay. So we have an order of the sample and they are randomly selected. But non-parametrics are not as good as parametrics. Parametric tests are more powerful than non-parametric. So when you get a p-value, provided you have applied the correct test, then the p-value has more power, more likelihood of being true than non-parametric. So non-parametric has less power. Okay. So this is the basic difference between the two types. So again, I've repeated this just for your this thing. So you got the t-test, which I told you, and then you got the one-way analysis. Okay. The correlation, Pearson's correlation, we have not yet covered. So we haven't done correlation and regression. So leave these two away, the Pearson and Spearman. And on the non-parametric side, we spoke, there is Wilcoxon, there is Mann, Whitney, Yu, and Cruxall, Wallace. Okay. And we also said Friedman's. Okay. If you want to know more types of parametric tests, then the Fisher's exact test I told you yesterday, which is used for small samples. Okay. So this is the way you've got it all written out. So you don't really have to worry very much. The statistical guide will actually tell you if you know what your data is, whether it's nominal, ordinal, whether it's discrete or it is normal, then you have got clear-cut guidelines of which test to use for which type of data. Okay, so it's quite important. And again, we've got a big outcome. So we got a big chart, and this chart it tells you, what is the input variable that you're working at. So whether it's nominal or whether it's ordinal, things like that. And on the other side, what is the output that you're looking for? And depending upon the two, it works out which test to do. Now, this is not something that you have to worry very much about. All you have to know is normal distribution, parametric, skewed distribution, non-parametric. It's very, very simple. Okay, that's why I tried not to give you more information on these tests, because it confuses you more than it helps you. So that's why it's not important to know the details of the test. All you need to know is what to do, where to do, and when to do. That's it. Okay. So did this help a little bit? Is it clear, the concepts I just said? Hello?
Yes.
Yes.
Yes, sir.
Okay. So now let's continue the lecture where we left yesterday. Okay. So we said that we have done the first 3 parts. Now we've got 4 more parts to cover in statistics. So let's look at comparison risk. How do we compare risks between 2 groups? Okay. So there are 2 or 3 tests which are available. One is risk ratio, and the second is odds ratio. So I'll explain each one of this in detail, and this is very interesting, and it will clarify all your doubts as we go along. There is a concept called as risk reduction. There's a concept called as number needed to treat. And similarly, there's a concept called as numbers needed to harm. Okay. So risk ratio, odds ratio is what we have to focus on. So let's look at risk ratio. Okay. So what is risk? In statistical language, we are not talking about general medical language. In statistical language, risk is the probability that an event will happen. Very simple. So that is what we mean when we say risk. Okay. It is calculated by dividing the number of events by the number of people at risk. Okay. So I'll get some figures out in a minute. So it's calculated by dividing the number of events by the number of people at risk. Simple. Okay. Straightforward. So if one boy is born for every 2 births, okay, the probability or the risk of giving birth to a boy is 1 divided by 2. So number of risks divided by total number of people that can be affected. So 1 divided by 2. Okay. So not 0.5. Clear? Very straightforward. Okay. So if you go higher, then the number changes. So if 1 in every 100 patients suffers a side effect from a treatment, then the risk is 1 in 100, which is not 1. Okay. And I've given this higher number for a reason, because I'm going to talk about odds ratio in a minute. Okay. So the risk ratio, what does it mean? The risk, it actually calculates the risk for an event happening when you do something. So it's simple words, is the risk of death while traveling to the shop to buy a lottery ticket is higher than the risk of winning the lottery ticket. So that is why it's important to calculate risks when we are talking in statistical terms, because within the same event, there are 2 things that are happening. Okay, one is you're traveling and one is you're buying a lottery ticket. And until and unless you define the risk for traveling and define the risk of the lottery ticket, your statement in a statistical method will not make any sense to the audience. That is why you have to use the risk ratio. So this is how you make the statement. The risk of death while traveling to the shop to buy a lottery ticket can be higher than the risk of winning the lottery. This is how the bottom line of your paper will state. Okay. And so this is how you have to work risk ratio. When is it used? Relative risk is used in cohort studies and in prospective studies. I spoke about cohort and prospective in the last lecture. And they are used in cohort and prospective studies that follow a group or a cohort over a period of time and investigate the effect of a treatment or a risk factor. Okay, so you've got a group, you're giving a treatment, but you need to know whether what is the possibility of the treatment working or not working, what is the risk of a treatment of a patient getting better or not getting better. So that's how risk ratio is decided. Okay. So these are calculated, the ratio is calculated by dividing the risk in the treated or exposed group by the risk in the controlled or unexposed group. So in the first instance, you calculate the risk in the treated group. So number of events divided by total number of the group will give you the risk. Then you go to the control group and you calculate the risk in the control group. What is number of events divided by total number of in the group. And then you do this number which comes out, that risk divided by this risk gives you the risk ratio. Okay, I'll show you an example. So the risk of an event happening in one group divided by the risk of it happening in another group. Okay. So if risk ratio is 1, that means it's the same whether in group A or group B, then there is no difference in the risk between the two groups. Okay, because A upon B, both must be the same. That is why they have cut each other and the answer was 1. If the risk ratio is more than 1, that means the treatment group has a higher chance of having that risk. Okay, so the numerator is higher than the denominator, and the denominator is always the control group. Okay, so when the numerator, which is the treatment group, has got a higher risk than the denominator, then the risk ratio will be more than 1. Okay, similarly, if the numerator is less, which is the treatment group, than the control group, then the risk ratio becomes less than 1. Okay, so the rate of that event is reduced. This is how we write in the papers what is the value of risk ratio. So 1 is no risk or no difference between A and B. The risk is there, but there's no difference between A and B. More than 1, it is increased risk in treatment group as compared to the control group. Less than 1, the rate of the risk is less in the treatment group than the control group. Okay, so let's look at a few things. Always risk ratios are presented with their 95% confidence intervals. What I'm saying here is we always give values which will tell you that we are 95% confident that if these values of the given study were applied to the general population, this risk ratio will be true. Okay, so if the other important thing you have to remember is this is a fact now, I cannot change this. If the confidence interval for a risk ratio does not include 1, it is statistically significant. Okay, this is a fact of mathematics. So just remember this. So if a confidence interval for a risk ratio does not include 1, then it means it is statistically significant. Okay, so just stay with me on that. So again, now I'll bring back 2 slides which I showed you in the last lecture yesterday, which everybody got confused. So a confidence interval usually is said to be good in relation to a risk ratio when it is small or it is tight, when it is on the same side of unity. So on one side of 1 is a good confidence interval. If it is going beyond 1, if the confidence interval goes beyond 1, it's statistically not significant. If it is less than 1 or same side of unity, it is statistically significant. And the third number that you have to remember is if it is less than 0.85, it also becomes clinically significant. Okay, so just these are facts, you cannot change it. Don't ask me why. This is a mathematical fact. So if confidence intervals does not touch unity, it is statistically significant. If it is beyond 1, it is not significant, as I said that. If it is on the same side of 1, it is statistically significant. If it is below 0.85, it becomes clinically significant. So I'm bringing back one slide from before, which will now start to make sense. This is the risk ratio for this group of patients. This was a cholesterol study which we looked at, and we were looking at what was the risk of cholesterol causing hyperlipidemia and hypertension in a group of patients as compared to a control group. So there are 5 studies which have looked at this, and these are 5 different risk ratios which have been documented, and they have also documented confidence intervals of these. So now you start to understand what I was saying the other day. So we said, if who's scratching? Don't scratch on the screen, guys, please. Okay. All right. So we said that if confidence interval touches beyond 1, it is statistically not significant. So A, not significant. Okay. If it is less than 1 or same side of unity, but not touching 0.85, it is statistically significant, but clinically not significant. If it is less than 1, but touching 0.85, it is statistically significant, but may be clinically significant because it is touched 0.85. This one is touching 1, so not statistically significant, but maybe it's touching 0.85, so it may be clinically significant. And this one is not touching 1, so it is statistically significant, and it is less than 0.85, so it is clinically significant. So in one graph of a forest plot, we have shown you everything, all the data with 5 studies, and given you almost a paragraph worth of description in a graphical representation. So this is how you interpret data, is the graph has to be represented. So in the exam, if I give you this graph, and I will give you this graph, that is what we do. We give you this graph, you have to look at the graph, and you have to tell me everything that is here at the bottom. All this that I said has to be said only by looking at this graph. So this bottom half doesn't come. Only the graph is given to you, and you're asked. So you're going to start with saying, this is a forest plot. This is what it is. This is a risk ratio. You can see here, it is said there's a risk ratio. There's a confidence interval defined for each of these studies. These seem to be 5 studies, which probably are part of a meta-analysis. The risk ratio has been defined on this with confidence intervals being defined. The first study is touching 1, so it is statistically not significant. And it's not touching 0.85, so it's clinically not significant, and so on and so forth. And usually at the bottom, if it is a forest plot, then at the bottom you will have the diamond, which is a cumulative of all of these, okay? And so the cumulative diamond is the final answer of the meta-analysis on the basis of the 5 studies that have been put up on display. Okay, now please tell me whether you understood or did not understand.
Understood.
Understood, but need to practice.
Understood. Understood.
Yeah, is it clear? This is how the graph
Yes.
will be given to
Yes,
you.
Concept is clear.
And you need to talk to me about the graph. And I spoke for 5 to 7 minutes
Yes.
only on the basis of this one graph. You understood that? So this is important to say. You must learn, practice every time. The only way to practice statistics is to take a graph and read out to me what is the interpretation of that graph. So this is why I put this up here. So you have to read out to yourself or to me what is the interpretation of this graph that I've put up here. But until and unless you know what is confidence interval or what is risk ratio, you cannot read out this graph. Okay? All right. Make sense so far? It's very important what I just told you. This is how the FECTS exam goes, FEBTS and FRCS also. I have been asked personally graphs in the FRCS exam. Okay? So be very, very careful. This is the way you have to practice. So let's give you an example of a risk ratio. Again, most of my slides are from that book, Medical Statistics Made Easy. So when you go back and revise, keep the book open and go through this, and it's easily available. The PDFs are available on the internet if you want. So just sit with that and try to understand what I'm trying to say. So let's look at an example, okay? So you got 1,000 football players and 1,000 non-footballers, okay? Now, we did a 1-year follow-up of both the groups. 12 footballers had broken legs, had fractures. 12 footballers. 4 in the non-footballers had fracture. So the question is, does football increases the risk of having a fracture leg? Okay, that's the question. So the risk in a footballer's group is 12 divided by 1,000. Okay, 12 divided by 1,000, which is 0.012. The risk of a non-footballer's group is 4 divided by 1,000, which is 0.004. So what will happen is, I'll give you just the first data, first 4 lines of the data, and I'll tell you what's the risk ratio of this group, having football being football being the cause of fracture. So this is how you calculate. First, you calculate risk of footballers, then you calculate the risk of group B, and then A over B. Okay, so 0.012 divided by 0.004, which is 3. And then I'll give you the confidence interval. And the confidence interval is 0.97 to 9.41. But most of it is way out beyond unity. And one of them is touching unity. Can you see that? It's 0.97 will touch unity. It will cross unity. So not significant. Statistically not significant. And this is so wide out that you need to investigate this further. You need to understand, what is happening in this group. So it is not significant, but this confidence interval is too wide. And if it is so wide, then you need to know further. You need to do more tests in the group to define what is the difference between A and B. Did you understand this? Yes or no?
Yes, sir.
Yeah, don't question me on the numbers. The numbers have come out of the software. So why confidence interval came from 0.97 to 9.41 is not the question which I have to answer. That has come out of the numbers, okay? So that is what you have to do. The computer calculates those numbers, and then you have to interpret those numbers. So that is risk ratio. Let's look at another concept called as odds. Okay, so we've done risk. Now what are odds? Odds is the number of times event happens divided by the number of times it does not happen in a group of patients. Is different from risk. Risk was number of risks divided by total people in the group, whereas odd is number of times an event happens to the number of times it does not happen in a group of patients. I'll explain this more. Stay with me. So odd and risks are more or less similar when you are considering rare events. So when it is a rare event, a smaller group, a smaller number, the odd and risk calculations will come out to be quite similar. But when the group size increases, or when you get to more common events, then the odd and the risk separate out. The concept of odd and risk separates out. And so that is why it is important to understand both the facts, okay? So winning the lottery is a rare event. Not winning the lottery is a common event. So the odd and risks of these will be substantially different. And you have to calculate that out. So let's look at the same example, okay? We said one boy is born for every 2 births. The risk of that group of one boy being born is 1 divided by 2, which is 0.5. But in this group, one boy is born and one girl is born. One event was the odd and one event was where the odd did not happen. So one boy was born and one boy was not born. So it is 1 divided by 2, 1 divided by 1. Risk would be 1 divided by total group, whereas odd is 1 divided by 1 because one boy was born, and more importantly, one boy was not born. So that is how odds are calculated. So 1 over 1 is equal to 1. Okay, that's the difference. So look here, again, I put the two side by side for you to understand. So odds is 1 event happening divided by 1 event not happening in the same group. So 1 over 1. Whereas risk is 1 event happening over total number of events happening. 1 over 2. Okay. So let's carry on. So 1 in every 100 patients suffers a side effect from a treatment. The odds are 1 over 99 because 1 had the side effect, but 99 did not. As opposed to this, if you were calculating a risk, it would be 1 over 100. You understood that? So this is how you calculate the odds and risks. So when is it used? It's used by epidemiologists when they are looking for factors which do harm, and it is a way of comparing patients who already have a certain condition with patients who do not have the condition. So it's like a case control study. So within the group, there's a group which has the disease, and the group which does not have the disease works as a control for that group, for the first group. Okay, so a case control study usually comes up with odds ratio. So the odd of an event happening in one group divided by the odd of it happening in another group. Okay, that's how you calculate. What do you mean by odds ratio of 1? Odds ratio, when it is 1, it means there is no difference in event between the groups. The odds in each group are the same of an event happening. If the odds ratio is greater than 1, the rate of the event is increased in patients who have been exposed to the risk factor. When odds ratio is less than 1, the rate of that event is reduced. Okay, so less than 1 reduced, more than 1 increased, 1 no difference between A and B. So odd ratios are also given with their 95% confidence interval. So any odds ratio that is thrown at you, you have to give a 95% confidence interval so that your study can be applied to the general population, to the true population, so that you can become 95% confident that the answer that you have received of the odds ratio can be applied to the general population. If the confidence intervals for an odds ratio does not include 1, it is statistically significant. Okay, this is important. This is a biological fact. So examples: 100 patients with knee injuries matched for age and sex versus 100 patients with no knee injuries. In group 1, 40 people did skiing and 60 people did not. So the odds is 40 over 60, not 40 over 100, but 40 over 60. The risk would be 40 over 100, but the odds are 40 over 60, which is 0.66. In the control group, 20 patients skied and 80 did not. So the odds are 20 over 80. The risk would be calculated at 20 over 100. The odds are calculated at 20 over 80. So you got 0.25. The odds ratio is 0.66 divided by 0.25, which is 2.64. Okay, this is done by the computer. And then the 95% confidence interval came out to be 1.41 to 5.02. Okay. Since this does not include 1, it is statistically significant. The skiers are more likely to get a knee injury than non-skiers. That is the statement you make at the end of this analysis. This is how you will have to analyze. So we will give you the first 3 lines and say, give me the analysis. What is the odds ratio? And can you tell me if skiers in group 1 are more likely to get knee injury? Okay, that's how the question comes to you in the exam. Some authors will write the odds ratio as percentages, okay, in their papers. You have to understand this, that actually some people will change it into percentages. So odds ratio of 2.64, if you calculate it with percentage, it is written as 164% increase in the odds of knee injuries. Okay, so very important to understand when people present percentages in the paper rather than odds ratio. It's always better to look at the odds ratio themselves. Okay, so odds and risks, similar values when we consider rare events. I said this earlier, but maybe substantially different for common events. And this is, again, I'm repeating this purely for your understanding. In some case controls, look for odds ratio rather than risk ratio. Odds ratio gives you a better understanding of what is happening in the group rather than risk ratio. Okay. Everybody okay? It was clear or difficult?
Yes, sir.
Yeah, it's not an easy concept. It confuses you, but I've tried to simplify it as much as possible. You will not understand straight away, and it will not come in the lecture. You have to go back and make up your own mind about it. Okay. So let's look at the next concept. Okay. ARR, NNT, and RRR. Absolute risk ratio, relative risk ratio, number needed to treat. They are used when an author wants to know how often a treatment works rather than just whether it works. Okay, so one answer is that giving paracetamol reduces fever. But when you want to know in how many patients does, or how much percentage can paracetamol reduce fever, then you have to use these numbers. Okay, ARR, absolute risk ratio, numbers needed to treat, and relative risk ratio. So let's understand that now. So risk reduction and numbers needed to treat are helpful in trying to work out how worthwhile a treatment is in clinical practice. Okay, please, this is the whole concept of doing all of these things. So these 2 things are important when you're trying to work out whether a treatment. So at this moment, the one paper you must read is just been published in New England Journal of Medicine. And the paper is whether hydroxychloroquine works in COVID patients, COVID-19 patients. So they have looked at risk reduction, number needed to treat. So if you haven't read this paper, please go and read this paper. Just been published in New England NEJM. Does hydroxychloroquine reduce risks in COVID-19? Okay, so then you use this sort of an analysis. So what is absolute risk reduction? Is the proportion by which an intervention reduces the risk of an event. Okay, so the proportion by which an so here you've got a number saying how much percentage will it reduce the risk when you do an intervention. Okay, quite important to understand this concept. The number needed to treat is the number of patients that need to be treated for one patient to get benefit. Okay, so you may, the lesser the number to be treated for one patient to get benefit, the better the treatment is. Okay, ideally it should be 100%. That means every patient who gets the treatment gets benefit. gets benefited. Okay, so number needed to treat is a different concept. Absolute risk reduction means the difference between event rate in the intervention group and that in the control group. Okay, that is the definition of absolute risk reduction. It's a difference of the event rate between A versus B. Again, we are talking about numerical values here. Okay, it is the reciprocal of NNT. Okay, that's also another important concept and is usually given as a percentage. So if you reduce the risk, the number needed to treat will go down. Okay, so it's important to understand this concept. Higher the ARR, lower the number needed to treat. Yeah, so that's why it's a reciprocal of number needed to treat. So ARR is usually calculated as 100 divided by NNT. Absolute risk reduction is calculated as 100 divided by number needed to treat. Let's look at relative risk reduction. The proportion by which an intervention reduces the risk of an event. So let's look at this. Okay, this is the example. Now you will start to understand what we are talking about. So 100 women with vaginal candida were given oral antifungal. 100 were given placebo, and they were reviewed 3 days later. Okay, this is the results. These are facts. These are all data that you've just filled in. So absolute risk reduction is improvement rate in the intervention group. This is the intervention group. This is not an intervention group. So absolute risk reduction is improvement rate in the intervention group minus the improvement rate in the control group. So 80 minus 20, okay, is the 20%. 80 minus 60. So 80 minus 60, which is 20%. Okay. NNT, numbers needed to treat. We said ARR is 100 over NNT. So NNT is 100 over ARR. So 100 divided by 20, which is 5. So the statement that you make out of this graph, which will be given to you, you will just get this paper and you will be asked to tell us what do you interpret from this graph. The statement is 5 women have to be treated for 1 to get benefit. You understand? That's how statements are made in clinical papers. Whenever you do your statistics, the discussion part or the conclusion is based on statistics, and the conclusion has to come out of statistics. So if only if you have done this calculation, will you be able to make this statement that 5 women have to be treated for 1 woman to get benefit. Did you understand this concept? Yes or no?
Yes.
Hello?
Yes, sir.
Understood.
Yeah. Is it getting confusing or is it okay so far?
It is okay.
Okay, so
You will not grasp everything straight away. Just stay with me. You have to keep going back and looking at it, and then it will click in your brains. Somewhere it will click. All I'm trying to do is I'm trying to just light spark. I'm going to give you the spark and you have to catch the fire. Okay. I cannot clarify in your brain straight away. Okay. Yeah, sorry.
Once again, sir.
Once again. Go back and read it. This is being recorded. So don't try to remember it now. Go back and listen to the lecture again. Okay. All right. Let's look at relative risk reduction. So the same group, same data. Now the incidence of candidiasis was reduced from 40% in the placebo group to 20% with treatment. You agree with that? So it was reduced 40 over 20 by half. So the relative risk reduction is 50%. 40 over 20, so 50%, right? That's how you calculate relative risk reduction. Okay, all right. So lower the number needed to treat, better. I said this before. You need a lesser number to be needed to be treated for a treatment to become better, to be acceptable. But look at the context. Always it is not true. You have to look at the context of it, okay? So if number needed to treat is 10 for treating a sore throat with a very expensive antibiotic, then that is not attractive. But if it is 10 for prevention of death from leukemia, then that is a worthwhile. So number needed to treat depends on the context in which you are talking. What is the treatment that you're going to use? So though 10 may be a low number, but using a very expensive antibiotic is not good enough. Whereas if you can manage to save life, then it is worthwhile. So always, whenever you read a paper and you look at number needed to treat, look at the context in which the NNT has been stated. Okay. The same concept of NNT is also extended to a concept of number needed to harm, NNH. Okay. NNH, similar concept. So NNH is the number of patients that need to be treated for one patient to be harmed by the treatment. So it is a similar concept, except that instead of treatment, we are talking about patients being harmed. So some papers may actually talk about NNH. That is why I've thrown it into the mix, so that you don't get thrown off when you see NNH instead of NNT. Okay, all right. Simple. Odds ratio, risks ratio, numbers needed to treat, absolute risk reduction, relative risk reduction. 5 concepts which you need to understand. Even if you don't understand now, it's okay. It's absolutely fine. You need to go back and listen to my lecture and sit with your book, and it will suddenly start to make sense. Okay. All right. Let's move on to the next. So out of the 7, we covered 4 now. We've got 3 left to go. What about statistics that analyze relationship? Okay. So there are 2 types of statistics that analyze relationship. One is correlation and one is regression. How is A affected by B? Okay, so let's look at that. What do you mean by that? When there is a linear relation between 2 variables, just a simple example, if blood sugar goes up, HbA1c goes up. There's a linear relation, okay, between variable 1 and variable 2. So that's the easiest one to understand. So there is, whenever there's a linear relation between 2 variables, there is said to be a correlation between them. Okay. So if one goes down, the second goes down. If one goes up, the second goes up. So things like height and weight in children are classical examples where you use the concept of correlation. Socioeconomic class and mortality. Lower the socioeconomic class, higher the mortality. This has a reverse correlation. The correlation doesn't have to be in the same direction. It can be in the opposite direction. So higher the socioeconomic class, lower the mortality. Lower the socioeconomic class, higher. So correlation can be both the directions. It can be in a positive way where one goes up, the other goes up, or it can be reverse where one goes up and the other goes down. Okay. So a strength of correlation between the 2, how closely they are correlated, is called as a correlation coefficient. Okay. So that's just a concept that you have to remember. So a correlation coefficient is usually denoted as R, small r. Okay. So the paper will say R equals 0.8, and you have to interpret what does 0.8 mean. Okay. So I'll talk about it in a minute. We'll go ahead and carry on, and then we'll understand what an R is. So positive correlation means when one goes up, the other goes up. Blood sugar goes up, hepatitis A, HbA1c goes up. Positive correlation. Line on the graph will slope from left to right. If you draw a vertical axis and a horizontal axis, blood sugar on one axis and HbA1c on the other axis, the line will start from left to right and go up. Okay. So the graph slopes up. Negative correlation, when one goes up, the other is down. Again, you draw an x-axis and a y-axis. So when x is less, y is very high, okay? So the graph slopes down from left to right. So there's a difference in the two graphs. One comes going up from left to right, and the other one comes from top to bottom. So a reverse graph, okay? And I'll show you examples. Okay. Now the correlation is very important, okay? So the correlation coefficient is quite important. What is the, A versus B, what is the correlation? So if R is more than 1 in the paper, whenever you're reading a paper and the correlation coefficient is more than 1, it tells you that this is a positive correlation. In this situation, the graph will go up from left to right because x-axis is low, y-axis is low. As x-axis increases, the y-axis increases. Okay, so that is a positive. So R equals 1 is a positive correlation. R equals -1 is a negative correlation. Whenever the paper talks about -1, R equals -1, this is the interpretation that should come in your mind, that they are talking about a negative correlation. And when R is equal to 0, between the two, there is no correlation. Effect of one does not affect the other. A flat line, it doesn't make. There is no correlation. It will be randomly scattered on the graph. Okay, we'll come to the graph in a minute. Okay, so R from 0 to 0.2 is a very low and probably meaningless. R 0.2 to 0.4 is a low correlation. So further away you go from 0, the correlation increases. Okay, so if it is 0.4 to 0.6, it's a reasonable correlation. If it is 0.6 to 0.8, it's a high correlation. And if it is 0.8 to 1, it's a very high correlation. But very high correlations are usually a warning. So it is too high, check for errors. Okay, there could be other reasons. Your test may not be right. The same thing will work on the negative side. Okay, so if you go minus, then the same thing works. So its correlation can be positive, can be negative. So important to understand a low correlation, a reasonable correlation, and a high correlation. Anytime it goes towards 1, something is not right. It is statistically not possible. It is possible, but your warning sign should come up whenever you read a paper where R is reaching 1. Okay, all right. So see, this is the paper. This is what I was talking about: blood glucose versus HbA1c. On the x-axis is blood glucose. On the y-axis is HbA1c. So today my blood glucose was 5 and HbA1c was 6. But last night my blood glucose was 24 and HbA1c was 14. So this is a positive correlation going up. As blood glucose goes up, HbA1c goes up. Okay, so when you did the calculation in the statistical package, you got an R of 0.88. So you will be thrown this graph, and at the bottom it will say R is equal to 0.88, and you have to talk. Then you have to say this is a correlation graph. Okay, this is a correlation package where, and it is a positive correlation package. And because R is equal to 0.88, it shows a very high correlation. So either this is factually correct or there is some error in the statistics. I need to look at the statistics again. You understand that? I'm not saying that R equals to 1 never exists. It does exist. But the higher the correlation, more you have to be wary that something is wrong. Okay. Did this graph make sense? It's called as a scatter plot.
Yes.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Scatter
Yeah,
plot.
very important to understand this concept. Okay. So now you have understood correlation. It will become very easy to understand regression. Okay. So let's go ahead. This is no correlation. R is minus 0.34. So it indicates it's a negative correlation. That means A increases, B goes down. But it's not a strong, it's a low correlation. It's 0.34. You understand that? And so stronger the correlation, more tight will be the plot. Stronger the correlation, more closely placed together will be the scatter plot. Lesser the correlation, more randomly placed will be the scatter plot. Okay? So it's body mass index versus activities. Excellent example of a negative correlation. All right, so whenever you see a graph with a scatter thing like this, you have to start off saying, sir, this is a scatter plot for body mass index versus activity measure. This is a correlation study. The correlation coefficient is minus 0.34, which suggests that this is a negative correlation, and the value suggests that there is a low correlation coefficient between body mass index and activity measure. This is what you have to say. Okay? All right. Good. Understood? Good.
Yes.
So it can tell how strong is the relationship.
Exactly.
But the problem is it does not tell the cause and the effect. Why A or what amount of change in A brings about the change in B. That is not told by a correlation thing. It only tells you that A changes, B changes. But it doesn't tell you what is the exact amount of change in A to bring about a change in B. So that's where you have to look at some other tests. I'll show you. Now, Pearson correlation is a method of calculating a correlation coefficient. Okay. But this works only when it is sampled from a normal population. So Pearson's correlation coefficient is a parametric test. Did you understand that? This is how you work it. So it's a correlation, it's a method of calculating a correlation coefficient, but values have to be within a normal population. Okay. Spearman's correlation coefficient is an estimation of coefficient for non-parametric variables. So Spearman is a non-parametric test. Okay. And don't worry about the details of the test. Just know the fact where Pearson's is used, where Spearman is used. The bottom line out of all of this is you will get an R value, a small r. And you have to learn to interpret what is that small r. What does a study mean when it's talking about a small r? So small r means that there is a linear relationship between two variables. Okay. So where there is a linear relationship between the two variables, there is said to be a correlation between them. Okay. And the correlation coefficient gives the strength of that relationship. Okay. Whether it's positive or negative. Some papers square the R. They make it R square. Okay. And when they use R square, it is always positive because minus into minus is positive. Okay. So they don't want to give you the thing. So it's very difficult when some papers has used R square. It's very difficult to know whether the graph slopes up or down because everything is positive in an R square. It does say that variation in one causes change in the other. That's all. That's all you can do. The closer the value of R square to 1, higher is the correlation. Okay, that's the R square. That's how you work out. So some statistics do not like the minus sign, so they square the value of R, and then it becomes R square. Okay, so if R square is there, then you have to just understand that there is a correlation. Closer the R square to 1, higher is the correlation. Okay, look at this scatter plot. Same scatter plot, fasting blood sugar, HbA1c. R was 0.88 because you were not sure what it is. So they've R squared it. So R squared is 0.77. So R square is minus 0.88 into minus 0.88. So 0.77. Okay. This means that 77% of the variation in HbA1c is related to the variation in fasting blood glucose. This is how you interpret the data out to me. Okay. 77% of variation in HbA1c is related to the variation in fasting glucose. Okay, all right. So we have understood correlation, or at least got familiar with the concept of correlation. So we go to regression. That's the next one. Okay. In regression, it's an analysis used to find how, the key is on how one set of data relates to the other. Okay. So it is particularly helpful when we want to use one measure as a proxy for another measure. Now stay with me on this one. Okay. So if a patient has had a test, has a bedside test versus a lab test, okay, and the numbers that you get, if you want to correlate the two numbers, the regression is used as an example. And I know you're confused, but stay with me on this one. So regression analysis is a technique for finding the relationship between two variables. Each of one is dependent on the other. So if one changes, the second changes. But we need to know how much is the percentage change in one to cause a percentage change in the other. That is where you use regression. Regression is more specific than correlation. Okay. So in a regression, same patient, scatter graph, fasting blood glucose on the x-axis, HbA1c on the y-axis, the regression line draws a line across the scatter plot. Okay. So it draws a regression line across the scatter plot. The moment you have a regression line, then anywhere on this graph, if it was a scatter plot, you cannot say what is the change in X to know what is the change in Y. But the moment you have a regression line in the scatter plot, it becomes numeric. And you can then say at 15, what is the HbA1c? So 10. You understand that? So this is the difference between coefficient and regression. Regression is specific. At 8, I can say what is going to be HbA1c. At 12, I can use the regression line to tell me what is going to be HbA1c. The scatter, if it was a correlation thing, I could not make a guess onto what would, the numbers that are not there in the graph, I will not be able to make a guess what is the thing unless and until I draw the regression line. The regression line is very important, and that is a different technique. Okay. And that's a linear regression. So fasting blood glucose of 15 can predict an HbA1c of 9.95. So you can actually use regression to predict what could be the value of the other factor. Okay. So the slope and the position of the regression line can be represented by the regression equation. Okay, this is mathematics, and this is how the equation is worked out. HbA1c is equal to 3.2 plus 0.45 into blood glucose. This is a mathematical calculation that is specific for every scatter graph. This 0.45 is called as the regression coefficient, the slope of the graph. Okay, how much degree slope is it? That is called as a regression coefficient, and that changes from study to study. So this calculation, they don't get hooked onto the numbers, get hooked onto the concept, how a regression line can help you predict what will Y be if X is so and so. Did you understand this? Hello?
Yes.
No?
Yes.
Yes, yes.
Yes.
Yeah,
Yes, sir.
yeah. I mean,
Yes.
some of you have understood good. Even if you don't understand it, go back and listen to my lecture. It will make sense if you're sitting with your textbook. Okay. So what's the difference of correlation versus regression? Okay. Correlation measures the strength of the association between the variables, but regression quantifies that strength. Okay. It quantifies, it gives you the exact value. How much change in X will give you a change in Y. It quantifies that association. Okay. And it should only be used if one variable is thought to precede or one variable is thought to cause the other. So there has to be a causal relationship between A and B before you can use regression values. Okay. So it's quite important that you must know that A causes B. So the correlation will tell you that there is an association between A versus B, And then the regression will tell you how much is the association of A versus B, okay, between two groups. Now, there are further techniques that are used in linear regression, and I'll just mention them. You just need to know that these are techniques of measuring the quantification of association, okay? So logistic regression is a variation of linear regression, usually used when there are only two possible outcomes, okay? So when either the patient can have disease or not have a disease. So whenever in a study there are only two outcomes available, you use what a technique called as logistic regression, okay? Poisson's regression is the frequency of rare events. So when you're talking with the rare events, fewer events, you use Poisson's regression. Classical example is using waiting times. Poisson is used a lot when you're analyzing waiting times for surgery, okay? All right. The more important one is the Cox regression model, okay? This is something that you must understand, Cox regression model. It is the effect of different variables on survival. Cox regression is a regression model, but it is used in survival curves. And when we talk about survival, we'll talk about this, okay? So the same technique, but used in survival. All right. So Poisson is usually used for waiting times. Logistic is used when there are only two outcomes, A or B. It's very specific. If there are, okay. So let's get on to the next one. So we have done coefficient and we have done regression. Okay, we did ratios. And now we come to the second last one, which is analyzing survival. How do you analyze survival? So there are various techniques available. One is survival analysis. One is life tables. One is Kaplan-Meier plots and Cox regression. I just told you about that, the Cox regression, okay? So when are these used? These are used when the time until a single event occurs and that event is death. It could be any other single event. For example, time until discharge, okay? So it's a technique that is used to define the time until a single event occurs, which means you're trying to predict the future. You're using the present data to predict the future, all right? And that is called as survival analysis. So situations in which the end event has not happened in every patient, has not happened, is the future. When information on a case is known for a limited duration. So at this moment, you know a little bit about the patient, but you're trying to predict a situation in future. That is when you use survival analysis. And censored observation means we've got limited of the duration observation. So a small period of time you observe the patient. A lung cancer guy came to your clinic, he got operated, you followed him up for 6 years. Okay, sorry, you followed him up for 3 years or 4 years, okay? But you are trying to give him 5-year survival. You're trying to give him 10-year survival. You're trying to give him 20-year survival. So the censored observation is because you only got 3 years. So there was a censor to the amount of data that was available to you. But using that data, you predicted the future. And that is what is called as survival analysis. Did you understand this concept?
Yes, sir.
Okay, all right. So two things, life tables and Kaplan-Meier plots, okay? So life table is a table of proportion of patients surviving over time. So look at the data. It looks at the data at a number of fixed points and calculates the survival rates at those points, okay? And the commonest one of life table, the outcome is Kaplan-Meier. So let's look at Kaplan-Meier. This is very interesting to understand how a Kaplan-Meier is plotted. So it recalculates the survival rate when an end event occurs in a data set. Okay, and I'll show you the graph and you will understand what I mean by this statement. That it's a dynamic graph. And every time in your group of patients of 100 lung cancers that you operated, when one dies, that gets plotted onto a survival curve and it changes the survival curve. So it is a dynamic graph, which each event, when it happens, recalculates the curve. Okay. So rather than happening at fixed intervals, it can happen, people can die anytime. So whenever they die, the Kaplan-Meier plot dips and there's a change in the curve. Okay. So look at this. So when you've got this curve, every single little dip on this little dip is a patient has died. Do you understand that? So this is what it means. So every event that happens, so there is no fixed interval, because here patients died sooner. Here patients died after a longer time. So every single event that happens changes the curve. So every one of this zigzag. So you can never draw a Kaplan-Meier straight. You can never. Kaplan-Meier has always got to have this zigzag quality about it. And then the cumulative effect of the zigzag gives you the curve. So every single dip here is a patient has died. Okay, every single dip. Can you see that? And that's how you calculate the Kaplan-Meier curve. So this is a Kaplan-Meier curve for somebody with rheumatoid arthritis. Survival over years versus cumulative survival. Okay, so they've gone here, starts with 100% and always dips down like this. With every death that is happening, it is changing. Okay, all right. So how do you interpret this is that at 20 years, 36% of these groups will be available. 36% of this group of patients were still alive. So Kaplan-Meier gives you prediction in future. Okay, so you can use the curve to predict what will be the outcome for this patient. Okay, it's also used to compare survivals between groups. It's a very, very good tool to compare A versus B in terms of survival. Excellent. The plot gives you a very clear pictorial representation of what is happening beautifully. So look at this, the same study, but now a subgroup analysis has been done. The men have been differentiated from the women. And very clearly, the moment you look at the Kaplan-Meier graph, you can now clearly say that at 20 years, 46% of the patients of women are alive, but only 20% of men are alive. Okay, so Kaplan-Meier curves can be used to compare treatments. So you can use it to compare surgery versus chemotherapy versus radiotherapy in treatment of lung cancer. So you will have 3 graphs, and if all of them come close to each other, then all 3 treatments are equally good. If there is divergence of the graph, then the one on the top is a better treatment because you have more survival than the one at the bottom. More people are dying with the one which is at the bottom. So it's very important. The Kaplan-Meier graph allows you to differentiate between various treatment modalities, or allows you to differentiate between different groups of patients having the same disease. Okay, did that make sense, guys?
Yes, sir.
Yes, sir.
This is a very important concept. Kaplan-Meier will be shown to you in the exam, and you need to tell us why it is zigzag. So, and you need to tell us how will you predict one versus another on the basis of the graph. Okay, so that's what we need you to do. So now don't worry about the names of the other tests. Log rank test is a test to compare the survivals between the 2 groups. It's just a technique, and you look at p-value, and p-value will tell you how significant the test is. Okay, this is just on the computer. You can use 2 groups, and you can put them through log rank, and you'll get a p-value. And if the p-value is significant, then A is better than B, or B is better than A, depending on whatever comes out. Okay, a Cox regression model. This is quite important. Cox regression model is used to investigate the relationship between an event, usually we're talking about that, to explain to possible explanatory variables, for instance, smoking status versus or weight. So let me just get more clarity on this. It provides us with the estimate of the effect. Okay, it provides us with the estimate. So remember, in the regression model versus coefficient model, coefficient only showed you A causes B, but regression showed you how much of A causes a effect in B. So that is what Cox does to survival curves. So when you apply a regression principle to a survival curve, then you get what is called as a Cox regression model. It provides us with an estimate of the effect that different factors have on the time until the end event. So, does smoking cause cancer? Does eating tobacco cause cancer? Does chewing tobacco? So all of these factors can be used in the same curve, and you can analyze it to give you a Cox regression model. Okay. So as well as considering the significance of the effect of the different factors, that is how much shorter male life expectancy is compared to that of the women, the model can also give us an estimate of life expectancy survival of an individual. So you can actually use a coefficient, a regression coefficient, to understand how much A will be at point B. So it's a future model, okay? The technique used is called as proportional hazard survival model. Okay, just take it. Don't ask too many questions. It's a technique on the computer where they use a hazard survival model, and what the result that comes out of it is called as hazard ratio. Okay, so the end result that comes out of the computer is something called as hazard ratio. Okay, and it's a Cox regression technique that is used. So what is hazard ratio? Hazard ratio is the chance, the hazard, something harmful happening of an event in one group of observations divided by the hazard of events in another group. Similar like odds ratio, okay? So the hazard of something harmful happening of an event in one group divided by the hazard of the same event happening in another group. So a hazard ratio of 1, when the Cox regression model using proportional hazard ratio gives you a HR of 1, it means that the risk is the same. Okay, the risk is 1x of group A as compared to group B. The risk is the same. If the hazard ratio comes 2, then it is twice the risk. Okay, so in one group of patients smoking, so in males, smoking may cause twice the incidence of lung cancer as compared to females. That is how you interpret hazard ratio. So if HR is 2 for a group of patients with males and females looking at smoking as a risk of lung cancer, then this is the interpretation that you have to make. Okay. Look at this, how Cox regression has been done. Okay. So this was the same graph I showed you earlier, men and women with the rheumatoid arthritis. This was the statement we made that at 20 years, 46% of females and 18% of men. Okay. Now we apply the Cox regression to this graph. So when you apply the Cox regression to this graph, the answer comes back as hazard ratio of 1.91. Okay, and a p-value of 0.05. This is the computer result which will come back after you've done the test. The proportional hazard test has been done. The Cox model has been applied. So how do you interpret this model? And this is for males, okay? So the interpretation is a hazard ratio of 1.91 means that the risk of death in any particular time period for men was 1.91 times that for women. Did you understand this? So when I give you this, the right-hand side, I want you to read the left-hand side to me. I want you to be able to tell me the interpretation of the graph, okay? And then because p-value is less than 0.05, one more line you can add is this is statistically significant. Okay, all right. Okay, so there we are. The same thing that I've explained, 1.91. So this is also given a confidence interval. Okay, so confidence interval that they have given is 1.21 to 3.01. So we are 95% confidence that in the general population, we're talking about the now you're applying the data that you have from your study to the general population, and you are saying, I am 95% confident that the true hazard ratio for the general population lies between 1.21 and 3.01. So you have to make that statement as well when I give you this chart in front of you. And then the p-value you have to say is statistically significant. Okay, so when this gets thrown at you, this is what is the answer which has to come out. The thing in blue is what I want you to say when white is given to you. Okay, all right. Degree of freedom is the statistical method for statisticians. They use is the numbers of independent pieces of information that were available for the statistician to make the calculations. You don't need to know too much about it. Just know that whenever a result comes in, there's always a degree of freedom by how much the statistician used, how many data points the statistician used to calculate these numbers. Okay, so it gives you details of what's happening with the statistical end. Okay, now the last one, which is quite important, is to analyze clinical investigations and screening. How do you do that? So when you're analyzing clinical investigations and screening, you're looking at sensitivity, specificity, predictive value, and level of agreement and kappa. Okay, so let's look at each one. So think of any screening test for a disease. The disease itself may be present or absent. Okay, the result test may be positive or negative. And screening, these techniques will actually give you answers to these questions. Okay, so you have to use a screening test and you have to tell whether the disease is present or absent, and the test has to be positive or negative for the disease. And it's the correlation between the two is what we talk about when we talk about significance. Okay, so look at this one. All right, it's a very easy to understand, beautifully placed out. So test result on one side is positive, negative. The disease on the other side is present or absent. Okay, you got A, B, C, D. Okay, forget the false, negative, false. Just stay with A, B, C, D. Okay, so sensitivity. If a patient has the disease, needs to know how often the test will be positive. Positive in disease. True positive in disease. Okay, so whenever you have sensitivity, I usually look at the N. So for me, sensitivity tells me how many positives are there in the disease. It's the opposite. So for me, a sensitivity of the test is the ability of the test to correctly detect the presence of disease, the positivity in the disease. So N tells you positive. Opposite, always the opposite. That's how you remember. Whenever we talk sensitivity of a test, it tells you how many positive cases will you find out using this test. So the way you calculate according to that table is, let's go back to the table. A divided by A plus C. A divided by A plus C is the way you calculate sensitivity. Okay, so it is the rate of pickup of a disease in a test. You will be given a table and you will be asked to calculate sensitivity of a test. What is specificity? Look at P. Easy way to remember. So the moment you get P, it talks of N, negative. So it talks of patients in whom there is no disease. Okay, lack of disease. So if the patient is in fact healthy, how often the test will be negative? Negative is the key thing in this. So P, negative. N, positive. Do you understand? That's an easy way to remember. So whenever you talk of sensitivity, you're trying to pick up how many patients are positive. When you're talking about specificity, you're trying to pick up how often the test will be negative. It's the opposite of P. So negative in health, and that is positive in disease. So sensitivity, positive in disease. Specificity, negative in health. So easy way is look at the P, look at the N, and that gives you the answer. as to what the test is, okay? And the way you calculate according to the table is D divided by D plus B, okay? And I should have put the table here for you to see it. The rate at which a test can exclude the possibility of a disease, okay? Negative in health always. Specificity P, negative in health, okay? That's the key thing. What is positive predictive value? If the test result is positive, what is the likelihood that the patient will have the condition? Okay. In this, the calculation is A divided by A plus B. Okay, I'll bring the table back up again. I think you need to look at that. So A divided by A plus B is a positive predictive value. The negative predictive value will be D divided by D plus C. So the number of times the test is negative, what is the likelihood that the patient will be healthy? Okay, so D divided by D plus C. So what is the interpretation? If the test is perfect, then sensitivity, specificity, everything will be 1. A perfect test. The lower the value of the test, less reliable is the test. Okay, so look at this. Same patient, same graph that I had before, but now we have put numbers into it. So sensitivity, we said, is A divided by A plus C. Yeah. So 20 divided by 25, not 0.8. Okay. A divided by A plus C. Yeah. So if gastric cancer is present, there is an 80% chance or 0.8% chance of the test picking it up. That's how you tell me. By looking at this graph, by looking at this table, this is how you talk to me. That in this table, if gastric cancer is present, the sensitivity of this test suggests that there is an 80% chance of the test picking up the disease. The same thing is looking at lack of disease. So D divided by D plus B. So 45 divided by 30 plus 45, which is 0.6. So sensitivity is, specificity, if the gastric cancer is not there, there is a 60% chance of the test being negative. Okay, specificity, if gastric cancer is not there, there is a 60% chance of test being negative. Negative in health, okay, very important. Negative in disease and positive in health, okay, very important to understand. So this is called as 40% will have false positive. 60 are truly being detected as negative. The outcome of that is 40 are falsely being detected as negative. So they are false positives. Okay, you've missed 40 cases of lung cancer. Okay, did you understand that?
Yes, sir.
Hello, yes or
Yes.
no? Or is it
Yes, sir.
Yes.
more confusing or less confusing?
That moment we
It's perfect,
understand,
sir.
We understood.
next slide we forget.
Okay. I don't know how to deal with that problem.
Yeah.
Okay,
We'll go
but
again
It
and again,
needs
sir.
revision. It
yeah,
needs
it
We,
needs
revision.
revision.
we require revision, sir.
Yes.
As long as you understand the slide when I present it, that's all I want to do.
Yeah.
I cannot expect you to remember it the next time. It's too much data coming together. But my job today is just to put it out there for you to go back and revise. Okay. Problem is, even when you read the simple textbook of medical statistics, it confuses you when you read a lot of the data together. So it's important. Each slide has to be taken separately. Okay. Positive predictive value. How do you calculate positive predictive value? A divided by A plus B. This one, the positive one. A divided by A plus B is 0.4. So the positive predictive value is there is a 40% chance if the test is positive, the patient actually has gastric cancer. Okay. And we come into the negative predictive value, the second line, D divided by D plus C, 45 divided by 45 plus 5 is 0.9. So there is a 90% chance if the test is negative, that the patient does not have gastric cancer. Okay, higher the number, better is the quality of the test. Lower the number, less reliable is the test. Okay, all right. But there's still a 10% chance of false negative. That's what you have to remember also. That 0.9 means 0.1% you're missing. Okay, all right. All right, let's look at the likelihood ratio. The likelihood ratio that the test result would be expected in a patient with the condition compared to the likelihood that the same result would be expected in a patient without the condition. So this is how you do it. You calculate the sensitivity and then you do sensitivity divided 1 minus specificity. So in our example, 0.8 divided by 1 minus 0.6, the likelihood is 2. So when you have likelihood ratio of 2, this is the answer. The test is positive in a patient. Patient is twice as likely to have gastric cancer than not to have it. So it tells you that it's a very, very sensitive test. It's a good test to tell you whether the patient's got gastric cancer or not. Okay. So let me just go through it again last time. This is the cumulative slide of all of them. It's very confusing topic, but let's get it. Sensitivity, N, how often the test is positive? N, P. So sensitivity is how often the test is positive if the patient has disease. Specificity, P, how often the patient is healthy. If the patient is healthy, how often the test will be negative? Okay, so negative and positive, N and P, opposites. Okay, so this is the way to remember. Positive predictive value, if the test is positive, the likelihood that the patient has the condition. Negative predictive value, if the test is negative, the likelihood that the patient will be healthy. So higher the number, better is the correlation. And likelihood ratio, if the test is positive, how much likely that the patient is to have the disease than not to have it. Take a snapshot of this or go back to this slide. This is the main slide. This is what will eventually tell you the answers to specificity, sensitivity, PPV, NNV, and LR. Okay. All right. Last concept, level of agreement and kappa, a comparison of how well people or tests agree and is used when data can be put into an ordered category. Used to look at how accurately a test can be repeated. For example, you did a test and you did it at Medanta and you also want to send it to Quest. Then you want to know what is the level of agreement between the results in Medanta and in Quest. Okay, so you will use statistics to give you that level of agreement. Kappa is the value that you use. So kappa can be 0 to 1. If the kappa is 0, there is no significant agreement. If no more than would have been expected by chance. So if kappa is 0, there is no agreement, okay, between the two tests. If kappa is 0.5 or more, it's considered a good agreement. A value of 0.7 shows a very good agreement, and kappa of 1 is perfect agreement. That means Medanta and Quest both gave same results. So kappa was 1. Okay, a perfect agreement between histology sample sent to Medanta lab versus sent to Quest. So in the paper, it will say the kappa was 1 between the two labs. That means both the test answers came back exactly the same. Both said this was thymoma B. Okay, so that's called as kappa. Kappa 1 is very good agreement between the two tests. So if the same cervical smear slides are examined by cytology department of two hospitals, K.03 is little agreement between the two laboratories. Okay, K.1 is perfect agreement between the two laboratories. So let me just go. This is all right. Ordinal data is what you use. And this is when it's continuous. Forget this. This is too confusing for you guys. Okay, let's look at this one. Prevalence and point prevalence rate. Prevalence rate is important. You will be asked in the USMLE, you're asked this. The existing number of cases of a condition at a single point in time as percentage of the population. So how many cases are there today? The number of cases of COVID today, it got time factor in 30% of the population, or in London population of 2 million, which is 30% of UK population. Okay, So it's a prevalence of a disease at one particular point as a percentage of the overall population. So at the time of the study, 90 people in a practice of 1,000 patients were suffering from Brett's palsy. Okay, just an example, a vague example. 15 were diagnosed in last year. 75 were diagnosed in previous years. Okay. So the the prevalence rate is 90 divided by 1,000, which is 90 divided by 1,000. But because you want to put a percentage, you have to multiply it by 100. So the prevalence rate is 0.9. Okay, 0.9. Now, if it is a chronic disease, then the prevalence rate is always higher because every year you get new diseases which get added to the prevalence rate. If it's an acute disease or short-term illness, the prevalence rate is usually lower than the incidence rate. Okay, so it's quite important to understand this. All right. I'm sorry, it is very exhaustive, but it is the truth, and that's what it is. Let's do sample size calculation. This is the last concept that I needed to cover in statistics. This is quite important. Again, everything that I'm saying quite important is something that can be asked in the exam. This is frequently asked in the exam. I ask this very often to candidates. How did you calculate the sample size for your study? If they tell me they've done a thesis, then I ask them, how did you calculate the sample size for your thesis? Straightforward question. And you'll be surprised, 9 out of 10 don't know. 9 out of 10 don't know the 3 factors they have to tell me. Okay, so I'll tell you what it is. The first thing is you have to talk about power of a study. Okay, so the power of a study is the probability that it would detect a statistical significant difference. Okay, so power of a study is important. If the difference expected is 100% cure with 0% cure with previous treatments, then a very small study is needed to detect sufficient power. You understand? So higher the power, lesser will be the sample size. Okay, so very important to understand this concept. If the difference is smaller, if you expect the difference to be smaller, then the sample size has to go up. It has to be a higher, bigger sample size. So more is the difference, less is the sample size. Less is the difference, higher is the sample size. Okay, so it's very important to understand how you calculate power. So if the number of samples is small, a significant trial may look statistically non-significant. So the number is very important. This is called as a beta error of power. And the power of a trial is always called as 1 minus beta. So 1 minus the beta error is called as power of the trial. Okay, and the usual power of a trial is kept at 80%. We want 80% power to be able to detect a disease in your group, or to detect a difference, not a disease, a statistical difference in your group. The second factor that I want you to tell me, so first I want you to tell me is power. The second thing that I want you to tell me is significance. Significance is the probability of getting the results if your null hypothesis is true. So if you're looking at a 5% significance, we will have a p-value of 0.05. So you decide what is the significance you want to give to your study, because more is the significance, then bigger is the study. Less is the significance, smaller is the study. Okay, and then the effect size. So if group A is effective in 30% of the population and the new drug is effective in 40%, then effect size is B minus A. Okay, so 40 minus 30, which is 10%. And if you want to do relative, then it's 30 over 40. Okay, I'm not going to go into details, but just know that these are the 3 factors. 3 factors. Whenever I ask you how do you do calculate sample size, you have to say, I want to look at the significance, I want to look at the power of the study, I want to look at expected effect size. I have calculated these 3. On the basis of these 3, I did a sample size calculation. Normally, power is kept at 0.8, significance is kept at 5, and whatever is the effect size that you want. Okay, so this is the formula. I want you to know this formula clearly. There is no doubt about it. So sample size and significance. Higher the significance, more is the sample size. Higher the power, more is the sample size that you need. If you want to power your study less, sample size will go down. So it is very important how much of a difference do you want to detect. So if you are happy with p less than 0.05, then that is acceptable. Okay, that significance is acceptable. Remember this formula, just stay with this. All this that I spoke has no meaning. This is the only thing that matters. Sample size is calculated by significance plus power divided by effect size. If you can tell me this in the exam, I will pass you. Okay. All right. Thank you very much. Come back and ask me questions. I'm happy to stop if you want, or I'm happy to finish this rest of the talk. Hello. Everybody's gobsmacked.
Yes, sir.
I'm very sorry.
Sir, hello, sir.
I am very sorry. I tried my best.
Yes,
Sir,
yes, yes.
it's very good lecture, sir.
It takes time to digest.
Yes, sir.
R is gone for a toss, actually.
My only question to you is, are you more confused or less confused?
No, 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 no. We are
Less
clear.
and less confused.
Less confused. Yeah.
Yeah.
Did it help? Did it help me doing this talk?
Yes, yes.
It stimulate go back to the journals and see the statistics and interpret it by own rather than reading the data.
It's not easy to give a talk of statistics online.
Yes,
I promise you.
difficult.
It's not easy to give
It's very difficult, sir.
because what I need is a blackboard and a white chalk, and I need to be able to draw things and explain to you as I'm talking. But the reason why I gave this lecture deliberately is because now it is out there, it will be recorded, and then you please go back and read. I saw a very good, Adnan actually put out a very good technique. He put the slides on the top, and then he put the book at the bottom. And as the slides were going through, he was reading the book. And I think that's a good way to understand. So now we have done all this hardcore work of statistics. Let us look at how do you interpret clinical trials. Okay, this is the crux of the whole Mahabharata was told because you need to understand this. How the hell do you interpret clinical trials? Okay, so now stay with me for another 15 minutes or 20 minutes. Okay, are you okay to stay or are you tired?
No, this is a
Please
core
continue.
topic. Very
Please
important
continue.
topic.
Most important.
Yes.
Okay.
Yeah.
So let's look at that. Whenever you read a paper, what you want to ask yourself is, should I change my practice? Agreed? Simple thing. That's the question you have to ask yourself whenever you read a paper. The problem is there are too many journals out there, too many easy ways of publishing data. Internet journals, online publications. Most papers that are being submitted are being published, unfortunately. The rejection rate decides the quality of publication. But a lot of people are paying the journal to publish their paper. So unfortunately, the quality of the research goes down when papers are evaluated. Because if you're going to pay $400, any journal will accept your paper. You understand that? So it is very important for a clinical practitioner to use a sieve and distinguish between gold versus sand. So when you go out there online and try to read papers, it is like a huge lot of bulk of sand and 2 or 3 nuggets of gold. And so what you have to do, the whole idea of me teaching you statistics is that I am giving you a sieve, and I want you to start shaking the sieve so that the sand goes away and only the gold nuggets stay there, so that you actually understand what is the good papers and what is a bad paper. Okay, so you should be able to distinguish a good paper from a bad paper and apply that research to your own practice. That is the whole idea. That's why you read a clinical paper. So whenever you read a paper, the first question you have to ask yourself is, are these like my patients? Whatever I'm reading the data, is this what I see every day? So you have to assess your own clinical practice. The subjects in the paper may be sicker or more complicated, or your patients might be sicker or more complicated, okay? Your patient's duration of disease may be longer. So always look at the demographics. Start with the demographics of the study. Look at the demographics, most important. If the demographics doesn't match your own demographic, this study is useless for you. Throw it away, okay? Because you cannot apply it to your practice. So look at this one. Non-intubated thoracoscopic lobectomy for lung cancer, okay? So you as a thoracic surgeon want to decide, should I start doing non-intubated thoracoscopic lobectomy in my cases of lung cancer? What will make you decide that I want to change practice? Besides, of course, that it is sexy and all that, that's different. But what will make you decide genuinely on the basis of research? So first and foremost is you have to, whenever you see a paper, always look at this table. Always, all papers have this table. And try to analyze this in terms of, are these patients similar to my patients? You know, do I really see these sort of age group? Look at your, where is it, lung cancers, they have tumor size. Are my patients of the same type? 2.1 centimeter, do I really see 2.1 centimeter tumors? Intubated, do I see 1. So this is how you decide. You look at, you match this data to your data. If it is similar, then you go ahead and read a little bit more about this paper. So the first question is, look at the demographics. Look at post-operative. Now, do you really see stage 1A cancer? If you don't see stage 1A cancer, 78.3% of this group was 1A cancer who had non-intubated lobectomy. Now, in your clinical practice, if you're seeing stage 3 cancers or 5 centimeter cancer, then can you actually start adopting non-intubated VATS for your practice? The answer is no. So you have to look at this. What is the staging at which these guys are operating? So very few advanced stages, almost all of them are early stages. So this is not like your own practice, okay? So very important to understand that. So what happened to the subjects? That's the next question you have to ask yourself. Whenever you're looking at a paper, look at what happened to the subjects. Always review what is called as a consort diagram. The consort diagram is a giveaway. It's surprising how many times people don't look at the consort diagram. This is a clear-cut giveaway whether the guy has genuinely done good research or not good research. A consort stands for Consolidated Standards of Reporting Trials. It is important to know this word consort, okay? And I'll show you that in a minute. So you have to look at how many people were recruited all the way to what happened at the end of the study. So you may start with 1,000, but if your study ended with 5 and you presented the paper with 5 patients, giving the assumption to the viewers that you're talking about 1,000 patients, then you're cheating the viewers, okay? So always follow it. Look at how many finally made it to the end. And that is the key thing. How many dropped out? That is one important factor. And most importantly, why did they drop out? Do you think they dropped out because they got negative results? A lot of people cheat. Every time they get a negative result, they drop the patient from the study. So they start with 100, and then if one patient has a complication, they will just take him out of the study. So a lot of papers cheat. So look for that. Dropouts are a key clue to understanding the quality of the paper. Okay. So doctors may delete patients due to lack of response. Okay. Because they start with one hypothesis. They don't start with the nulls hypothesis. They start with their own hypothesis that I want to prove that uniportal VATS is better than everything else on this world. So when you start with a hypothesis, you actually have to start that uniportal VATS is not good. That is a nulls hypothesis. But most people, when they write a paper, they start with uniportal VATS is the best thing to happen to mankind. And then when you go through the consort diagram, you'll find a lot of people have dropped out because somebody had a complication, somebody had a bleed, somebody had a incomplete resection margin. Those are not reported. Just the final 5 who did well get reported. So it's very important to look at the consort diagram. And I'll show you an example. Look at this one. Okay, this is how a consort diagram goes. Enrollment, allocation, follow-up, and analysis. All of them are represented. So look at this study. They have got context n equals 33. Sorry. Can you see that? Sorry, that thing is coming in my way. So look at this study. They started with n equals 33, but 12 got dropped out. Okay, 12 got dropped out from there. And eventually they reported on only 9. Okay, and then they will make a statement on the basis of 9, giving you the impression that this is a study which has looked at 33 patients. You understand? So that is very important. The consort diagram gives you a clue whether the guy is lying or not lying. Okay. The other thing that you have to look at is the study design biased. Let me move this out so you can see it. So in the study design being biased, you have to look at randomization. Is there good randomization for the study? Was there a comparative group? Have they just looked at one group, or did they compare A versus B? It's a lot of papers and presenters also do that. They present their series of uniportal VATs, and then they make a conclusion that uniportal VATs is very good for the patient. But did you compare uniportal VATs to multiportal VATs to open surgery? And if you have not done that, then your conclusion is wrong. It is not acceptable. So this is very important to understand, that did the study have a comparative group or not? That is very, very important. Was there a placebo group? That is again very important. So in our real life, the placebo group would be probably multiport or would be open surgery. Okay, so it's very important. What about the blinding? You know, was it a single blind, double blind? What was the quality of the blinding of the study? You've got to look at it before you can decide whether a study is good or not good. Did the study include intention to treat analysis? Okay, this is key thing. All randomized patients who are there should have intention to treat. That's the bottom line. All patients who are randomized should have intention to treat. Patients with no intervention received are dropouts. But very often, when the paper is presented or written, they take out all the dropouts, ignore all the dropouts, and all the statistics is done on positive findings. Okay, so if these are not included, if dropouts are not included in the intention to treat, then the whole results are skewed. You are massaging the statistics, and that's not good. More than 50% papers do this. They do not state the intention to treat. If you have stated the intention to treat, then the analysis should be all patients with intention to treat, whether they dropped out or didn't drop out, or whether there was a positive result or a negative result. So always when you analyze a paper, look for intention to treat. And at the end, look at how many patients did they base their data, their statistics on. If the final number tallies with intention to treat, then it's a good paper. It has to tally. It has got to include everybody who was included in the trial. You cannot do dropouts. That's the key thing. Okay. The other question when you look at a paper is this a superior paper? Is this a paper looking at superiority, which means A is better than B? Is it looking at inferiority? A is not better than B. Or is it looking at equivalence? A is equal to B. So superiority studies are common. Most of the people who come in and present papers and write papers, they don't start with the nulls hypothesis. They do not. They start with the hypothesis saying A is better than B, and then the whole paper is written on the basis of the hypothesis. A good paper starts with the null hypothesis and then tries to disprove the null hypothesis. That is the key thing. So read through the paper and identify, is there a null hypothesis? If there is a null hypothesis, then that's good. Superiority studies are commonly published. Equivalence or inferiority should be included in the analysis. That is the problem. Most people drop out. Anything that comes A is equal to B, they just drop it. Or A is less than B, they drop it from the analysis. So the 95 95% confidence interval may be less if you include everything in the thing. Sorry, if you exclude things. If you exclude things, then your 95% confidence intervals becomes narrow, because now you have excluded. So you are making a wrong assumption and a wrong thing. And then the sample size changes. Okay, your calculation completely goes haywire if you do not include equivalence or inferiority within the study. So that's very important to include all three within the study and to report on all three. Measurement of parameters, have they been defined clearly? Has the paper defined the measurement? Standard parameters of measurements have been used. The most important thing is the measurement able to correlate to clinical effect? Can I change this measurement? Whatever I'm doing, a biomarker, does it affect length of hospital stay? So the effect has to be in clinical effect for a paper to be really effective. And is it validated against international standards, or have they created their own standards? So you need a paper which is validated against international standards. You need a paper which will tell you that my findings have the following effect on the outcome of your patient. Then it becomes a good paper. Okay. Is the outcome meaningful? Which means, if you're using remission rate, recurrence rate, cure, yes, it is meaningful. You can apply it to your clinical practice. The problem is when they don't use meaningful data. Biomarker level may not, it doesn't mean anything. What does it matter if the biomarker is 5 or 100? Until and unless it helps me detect lung cancer, what am I going to do with the biomarker? So it's not about biomarker, it's the implication on the clinical effect that is very important. And surrogate markers are no good. If A is equal to B and B is equal to C, hence A is equal to C. That sort of analysis is no good, should never be used in a paper. Okay. Multi-center trials. Why do people do multi-center trials? Because we've understood that the sample size is key. Whenever you want to do anything, you want a good sample size. So if you're dealing with a rare disease or if you're dealing with a rare surgery, then you have to expand the sample size. So mesothelioma surgery, one center will hardly do 5 or 10 in a year. So you cannot do a trial on the basis of one center. So because you want more data, you make it multi-center. You want to include more patients, okay? The problem with this is that there is a lack of standardization between various hospitals. I may be doing surgery by VATS, somebody else may be doing it by open, the third person, a registrar may be doing the surgery. So multi-center trials have an inherent problem of lack of standardization. And protocols have to be very rigid. They have to be strictly followed if a multi-center trial has to be of good quality. So just because somebody's done multi-center trial doesn't mean it is good quality. You got to read between the lines of the multi-center trial to know whether it is worth it or not. The other thing is shifting targets. Okay, this is very important concept. The techniques improve. You may report on something and then techniques improve and another thing comes in. The problem is the technique may have improved, but did it materialize into incremental gain for the patient? That is the question you have to ask whenever you see a paper. Don't get fascinated by new techniques. Okay, new techniques are good, but does it mean that it is good for the patient or not? So look at this one, VATS, classic example. Multi-port versus two-port versus uniport. Can we say that it's actually making a difference to the patient? The technique is getting better, but can we say it is making a difference to the patient? Are clinical outcomes worth it or not worth it? That is the key thing, okay? So we've got multiple talks of these sort of papers. Robotic surgery is better than video assisted. Single port is better than multiple thoracoscopic port, okay? But when you go into the paper and you read it, there are no clinical effects seen. There are no comparison studies. They're just making an assumption without comparing A versus B. There is very little data. So, the way to do that is then to do a meta-analysis. So this is the one which we published. Meta-analysis of VATS versus robotics versus open. Within VATS, we also looked at uniport, multiport, and robotics. So a real detailed analysis of all the factors. And then you make a recommendation. You have to do the forest plot and you have to make a recommendation whether your technique favors open or favors multiport or favors uniport. So this is a paper that you must read. I recommend you read this paper to understand how statistics can be used to analyze a question. Okay, it's a very, very well done paper. I have to say I'm pretty happy with this paper. And read it to understand how we have used statistics to answer some important questions. So when I sit in the audience and I hear somebody talk saying uniportal is better surgery, I get very upset because there is no data. We have done analysis. We've looked at the data, and till the moment, it may be good for you, it may be good in your hands, but till the moment you can prove to me that it genuinely has a clinical benefit, don't stand up and talk about it. Just say it is possible and it can be done. So there's nothing wrong with the technique. You just have to say it is possible and it can be done, and it is something worth learning. Okay. The other key thing in a study is look at how the missing data is addressed. Very important, very important. This will give you a clue as to whether the statistics has been formed or not formed. What happened to the dropouts? So there are 3 ways of dealing with dropouts, okay? Listen to the 3 ways how we deal with dropouts in a study. One way is called as non-responder imputation, okay? In non-responder imputation, you study everybody. You study all the subjects, whether they are in or out, you study them because they were intention to treat. The problem with that is your success goes down because obviously your figures become less. The second way is it's called as a last observation carried forward, which means you study the patient up to a point, one patient up to a point, the other patient all the way through, but you decide whatever was the last observation of the patient, you carry it forward for all the subsequent observations. The problem with this is it increases the success rate, but leads to errors because you are assuming that this was the finding of the patient in future studies. And the third way is called as imputation, which means you estimate the results. You use a calculation to estimate what would have been the value of this patient if he had continued. And that is not good because you cannot estimate results. Because you can use all the techniques, but it skews the whole result. And a lot of studies do this. You find n equals 30 at the start. You find n equals 30 at the end. But out of that, 20 had dropped out. And those 20, they used an imputation technique. In statistics, you have an imputation technique where you can estimate the results. And until and unless you read carefully into statistical methods, you will not realize that the author has used imputation as a technique. And so he's giving you completely false results. Okay, so you have to be able to distinguish between this. So always look for dropouts. Very, very, very important. Another way to understand that there have been dropouts is to go to the registry, CTRI, okay, clinical trials registry. In this, all trials are registered. When you start a trial, you're supposed to register. And you have to review the website of CTRI. And immediately you will know how many patients were originally decided in this study. When they got the ethics committee approval, how many patients were decided? And then when they published the data, how many patients did they publish the data on? Very, very clear cut, you will know. The moment you look at the CTRI side and it spoke about 140 patients, and then the final paper came out with 32 patients, no good, no good. And you'll find that about 90% of papers do this. They start with the sample size calculation is high, but eventually when they report only with the very low numbers. And so completely the study is wrong and it's not a good paper to use. How good are the results? Is the author hooked on p-value? Is he all the time trying to prove p-value? Is he using, the moment somebody uses hundreds of tests, you must worry about the paper. Because whenever you have used hundreds of tests, it means one test did not give you the answer that you wanted. So you used a second test. So you used a third test. So you used a fourth test. People do this. They repeatedly put the data back into the thing. Let's try t-test. Okay. Now let's try Fisher's exact. Okay. Now let's try. So methodology of how they have calculated the p-value is very important. The p-value is biased in many, many, many papers. They've just used a test which has favored them rather than using the test which is needed for that particular data. So they are trying to prove that null's hypothesis is true. So very, very, very difficult. Okay. Look at this sample size. Okay. Now, n equals 50. They gave a study, published a paper. The first paper was completely published, saying that, you know, there is trending, significant trending towards difference. They showed this graph and showed that there is a lot of difference between the two. Though they could not get the p-value, they actually had the audacity to say that, you know, we are. But the moment the same study was done with 500 patients, the whole picture changed. Okay, there was no difference between the two treatments. Hence, it's very important to look at the values of sample size and look at the difference from the sample size. How big an effect? So always calculate numbers needed to treat. I told you about that. So in a GI bleed, this is just an example of how to do that. So absolute risk difference, and so numbers needed to treat are quite important to calculate. Always check the figures. Look for graphs. Graphs are classical example. Look for errors in the graphs. Very important. Lot of graphs have error. Look for axis manipulation. Sometimes people manipulate the axis to suit their results. So if that is done, that's not good. Look for lack of zero on the Y point or on the X point. If your study is not starting from zero, there is something wrong with the study. People have manipulated the data to give you the answer that they want. This was not based on null's hypothesis. And most importantly, look at confidence intervals. I have now clearly told you what is statistically significant, what is clinically significant. So look at, you know, whether is it touching 1, is it less than 1, is it on the same side of unity, is it touching 0.85, is it going completely beyond 0.85. So confidence intervals give you a lot of idea whether the paper is good or not good. Okay. So meta-analysis, a lot of people have this thought process in their mind that meta-analysis are the best, and every published meta-analysis means it is a good paper. Okay. So there is a lot of this thing happening. A lot of Chinese authors, I told you this before, they are collecting large data from many databases like the ESTS dendrite database or the SEER database, and then throwing questions at it, hoping to get an answer. And then, you know, it is called as massaging of the data. It's called as fishing. So they're fishing in the sea with a small net and hoping to get an answer. So a lot of meta-analysis published in the Chinese journals are completely biased. And this beautiful paper talks about it. And it says that really all meta-analysis have to be carefully looked at. More than half of them, 85.8% of meta-analysis were not properly done. 85.8% of meta-analysis in published literature were not properly done. So very important to understand what is gold and what is sand. Okay, all meta-analysis is not gold. That is what I'm trying to tell you. Now, this is a classic. This is from Alan Seo's talk. This is a classic paper, okay? It is the most rubbish paper you can ever come across because it says stereotactic ablative radiotherapy is better than surgery for stage 1 non-small cell lung cancer. A pooled analysis of 2. So if you look at the final analysis, they say that stereotactic SBRA is better than lobectomy for stage 1 non-small cell lung cancer. And it got published in the Lancet. For God's sake, the Lancet. It's not a joke. So now we have to look at why did this get published in the Lancet? And Alan has done a classic analysis of this paper, and he told us. So look at what the points he found. He looked at both the RCTs. He found that there was low recruitment in both RCTs, and there was early termination in both the RCTs. The follow-up was very short. It wasn't long-term. They just looked at, few months follow-up to say that CT scan is better. Okay, patient is treated. He's gone following the SBRT. There was no power calculation in the two randomized trials. And it was a retrospective pooled analysis. So they took one study, they took another study, put them together, and then did a pooled analysis, try to do something like a meta-analysis. There was no heterogeneity between the RCTs. Okay, there was absolutely no. The study design, the patient selection, the protocol, the surgical approach, and the follow, all of them were different between the two groups. The demographics was completely different between the two groups. There was heterogeneity between the trials because large number of institutions were, it was multi-center. And the protocols in each center was different for treating. Histological confirmation of the anesthesia of the lung cancer by biopsy was not required in one of the trials. Can you imagine you're doing a lung cancer study and you're not even looking for histological confirmation? The trial relied on PET, but SUV was not obtained on all patients. 27 patients were assigned to surgery, but 3 did not have their assigned surgery. They did not have lobectomy. They had wedge resections. 5 out of 27 patients has VAT lobectomies. And we know that VAT's lobectomy for a stage 1A lung cancer gives you excellent results. But they used open surgery as a surrogate marker to say surgery is bad for stage 1 lung cancer. And the morbidity and mortality in the surgical group that they put in the paper was very high than expected norm. We have less than 1% mortality in VAT's lobectomy for lung cancer. These guys were quoting 5 and 6% morbidity and mortality. So why was this published? Well, this got published because of impact factor. Okay, there is a concept called as impact factor. So the more controversial the paper, the more it will be spoken of in other papers. So all surgeons subsequent to this paper started referring to this paper and saying this was rubbish literature. Okay, so impact factor is calculated by total citations during the year of the articles in the last 2 years by total number of citable articles. So this is the numerator and this is the denominator. Okay, the first one is numerator, second one. So you want to increase the numerator and you want to decrease the denominator. The way to decrease denominator is to reject a lot of articles because case reports never get cited. You know, another paper will never give a reference of a case report. So case reports are straight away rejected nowadays. In all good papers, hardly anybody publishes case reports. So you reduce the number of articles, so increase your rejection rate, but more importantly, bring in papers which will be controversial so that other papers will quote that paper. So whenever from now onwards, anybody writes for a paper for surgery for stage 1A lung cancer, everybody quotes this paper. So automatically the impact factor goes up. So this is the way editors use the technique. So just because this paper is published in the Lancet does not mean that this is a good quality paper. It's very, very, very important to understand that. And you have to realize that when you're reading a paper, what is good and what is rubbish is very important. So I'm going to finish off by this last slide, which is evidence-based medicine is gold standard, but you need to know what you're reading is good quality. RCTs are better than case series. Meta-analysis can answer many, many questions, but a lot of meta-analysis are rubbish in the way they have been conducted. International societies and society guidelines do change practice, and please follow society guidelines. They are very important, okay? But remember, they are only guidelines. And if you want to use a different guideline in an individual patient, something different from the guideline, then always back it up with an MDT. Always, MDT is very good to support your decision making. Most important is audit your own practice. Please look at your own results. Don't keep doing what you are doing for the last 20 years. That is not acceptable. You have to audit. You have to keep changing your practice. You have to keep putting in new improvements. Very, very important. And anything that you do has to be evidence-based. In the examination, I want people to tell me whatever statement they are making, what is the evidence behind your statement. I don't care if it is controversial. If you can tell me a paper and a good quality paper, I will accept your answer. I will not question you. This is not a rocket science. This is, you know, it's art. Surgery is an art. It's not a science. So we have to give way for individual differences between people. And as long as people can come up with evidence to back their discussion, I am very happy to accept whatever they say. Thank you. Oh,
thank you, sir. Thank you, sir. This was super.
Thank you. It was excellent.
Oh my God, this is crazy, man.
This is excellent.
I'm going to pause the recording here. Okay.
Please. Yes.
All right. Fine. Now, who wants to ask any questions if you want to? Don't worry about the mathematical side of statistics. That's what I'm trying to tell you. My lecture was designed to make you understand the philosophy behind statistics. That's why I gave you 7 categories. and what are the tests in those 7 categories. Don't worry about the mathematics, because that is for statisticians. We are not statisticians. In this exam, we don't look for you to understand the formula. Some formulas are there and it is there. You can't change that. That's not for you. But look at how it has been applied. That is the key thing. Okay? All right. I'm sorry, it's
Yes,
a
sir.
very, very exhaustive topic. It's very boring and it does get confusing. From slide to slide, you cannot keep track of it. But the only way you can do it is if you keep reading it again and again. And not
Yes.
statistics. Don't read statistics. Read papers. Read papers and
Okay.
apply the papers. That is the key. Don't read statistics. You cannot remember 2 days down the road. You cannot remember what was the meaning of odds ratio or what was the meaning of ARR. But look at how it is applied in the paper. So read papers. I strongly suggest that you start reading papers, not textbooks. Okay, because really textbooks, by the time they are published, they're 10 years old. You know. By the time they make revisions and things are changing so fast these days. It's very hard to keep up with data. That's why for the exam, just follow one small guideline, key topics or important questions in MCQs. Just you need basic knowledge, but you need evidence. You need to know what are the new guidelines. And everybody must go to ESTS website, download all the guidelines. If you haven't downloaded the guidelines, no good. You should have done it by now. So every single guideline that's available in cardiac, every single guideline that's available in thoracic should be on your desktop. I have 2 folders on my desktop, which is guidelines. And then you have to listen to lectures from your seniors. See, I very often do lectures on guidelines. I don't talk about the details of the guidelines. I just tell you the points, 1 point, 2 point, 3 point. I want to make it specific for you to understand. So read the guidelines. Quite important to read the guidelines. Okay. All right. Anybody's got anything else to say? Lots of thank yous, but
Yeah.
I'm very sorry that this is not something where I can.
Beyond thank you, actually. It's
No, I
Beyond
can't
thank you.
sort
Yeah.
of suddenly make it really good, but that's my room.
Perfect.
That's my bright office.
Finally, the black background is gone.
Yeah, I took it out. I took it out because I was feeling really tired. Okay, questions? Anything else you want to ask? Any hot topics? Anything else? Who wants to ask anything?
We need to go through the presentation back.
well, what you have not understood is that this presentation stopped at thank you, but there are 100 slides after thank you.
Oh, what?
Those are the questions, right?
Those were the questions.
Questions. Oh.
Okay.
But I have decided to stop because I don't think you can handle it. You will all get
No.
Once
We need
not
time
today.
to digest.
You'll get
We need
Not
time to
today,
digest.
Go
tomorrow.
to the next 100 questions.
We can keep
Yeah,
one
yeah.
more session tomorrow, sir. We'll go
Yes,
through
we
both
can
the
do.
presentations.
No. Tomorrow, no.
No,
We need a break.
not
So
tomorrow. After 5-6 days.
Sri Krishna is doing a talk tomorrow
Okay, sir.
on tips and tricks for exam going people. Then Tuesday, I think Babatosh is doing a talk on the remaining cases that he did. So interactive cases. And then, sorry, I'm feeling very tired. Yeah. Okay. So, and then I will do something else. We'll see. I've got Nasser Yusuf who's going to do a talk on bilateral emphysema. I have got Paresh from the US who's going to talk on CA esophagus and gastroesophageal reflux disease. So we've got a lot of people who are ready to talk. But I don't think at the moment you're not ready for my next 100 slides.
No.
You will
We are
fall
a bit
apart.
gobsmacked. Yeah.
You will fall apart. But it's a difficult topic. I tried my best. The problem is when statisticians give these talks, they get so excited by the various tests that they focus on the test rather than the clinical side of things. And I tried to keep it to the clinical side of things rather than tests. And that book, which I told you, Medical Statistics Made, it's a BMJ publication. It's available online. Just do PDF and now hundreds of people have uploaded it. So you don't need to share it on this. Just download it from anywhere on the web. It's freely available. I read your
Extremely.
Vikas, I read your book on high value statistics. And
High yield bias statistics.
yeah, it is very difficult book. I have to tell you. I mean, I've been reading statistics for so long, but I found that book to be very, very difficult. Actually, it's not lucidly written. What was it called? As high value or high impact?
High yield biostatistics. That is what
High
people
yield
read.
biostatistics.
That is what people read when they are preparing for USMLE.
USMLE. It's there for USMLE, but but I'll tell you, that's a very difficult book to read. I found it to be really difficult. I read through it.
The book you gave is very good, sir. The BMJ
It's a
publication
very
thing.
simple. It's a simple, very lucid, and every clinician in the UK actually uses it. So we are quite happy to use it. What happened? Did we not relay to?
We did. What happened?
Yes, it was there in YouTube. I was seeing in
recording.
YouTube.
It was there in YouTube also, sir.
Yeah.
Okay. Yeah, because no, it's still live on YouTube. Okay,
It is still live.
No, we are not live.
No, it's not live.
It's not getting recorded. These are not getting recorded.
No, it's.
Oh, it is still live.
It's still live on YouTube, sir.
It is still live.
I don't know what it is.
Okay, I think you should take back as host. Is it? You can do it?
Yeah, maybe I need. Yeah. That's.
Yeah, I don't know how to give up.
Okay,
I don't know.
Let me see. Yeah, I need to take over the host, isn't it? 1 minute. Let me just.
Go to participants.
But I can't see. Usme hai nahi. Give up option is not there.
Sir can reclaim it. Sir can reclaim it.
So, yeah. So basically, I don't know how to give up.
It's okay. Don't worry. Reclaim host. Yeah, it is there.
Yeah, you do that.
Hey, I've reclaimed it.